Have you ever used an app that just works no matter where you are in the world? Whether you're in New York or Tokyo, it feels seamless. Well, that's the magic of distributed systems. But behind that magic, there's a fundamental challenge, a really tough trade-off that engineers at every major tech company have to deal with every single day.
And really, that whole trade-off boils down to this one critical question. Is it more important for your system to be perfectly 100% correct at all times, a single source of truth? Or is it more important for it to be always available, always on, even if the information it gives you is just a little bit out of date? This is the core conflict we're going to dive into.
All right, so here's our game plan. We'll start with the basic dilemma that every distributed system runs into. Then we'll introduce the rule book for all of this, the CAP Theorem. After that, we'll see this trade-off in action with a simple example, look at how real-world systems make their choice, and finally, explore how that choice totally shapes the technology they're built on. Okay, let's get right into the big problem. When you build any application that runs on servers all over the globe, you just have to accept one simple, unavoidable fact. The network that connects them is going to break. It's never a question of if, it's always a question of when.
This reality has a name. It's called partition tolerance. And a partition is just a technical way of saying there's a network failure that splits your servers into groups that can't talk to each other. Your system has to be able to handle this. It's the one piece of this puzzle that is absolutely non-negotiable.
And that brings us to the main event, the CAP Theorem. Think of it as the fundamental law of the land for distributed systems. It was first introduced by Eric Brewer way back in 2000, and believe me, it is just as important today. It lays out 3 key properties that any distributed system can have.
First up, we've got consistency. This one is all about correctness. It means that no matter which server you connect to in the entire world, you are guaranteed to see the absolute latest, most up-to-date version of the data. Every single read gets the most recent write, period.
Next, there's availability. This is the system's promise to be always on. It means that every request you send to a server that's working will get a response back. Now, it doesn't promise that response will have the freshest data, but it does promise you won't just get an error message. The system will always pick up the phone. And finally, we have partition tolerance, which, like we just said, is the must-have. It's the system's superpower to just keep on working even when the communication lines between its different parts get cut.
So here's the kicker. The CAP theorem says you can have any 2 of these 3 properties, but you can't have all 3. And since we already know that network failures, those partitions, are an absolute certainty in the real world, you have to pick partition tolerance. So this actually makes things a lot simpler. It boils the whole theorem down to one practical choice. When the network breaks, are you going to choose consistency or are you going to choose availability?
Okay, theory is great, but let's make this real. What does this choice actually look like? Let's imagine we're running a social media site and we have servers in the USA and in Europe to make sure the app is fast for everyone. So, in a perfect world, on a good day, everything's great. User A over in the US changes their name. That update gets sent instantly over to the server in Europe. So when user B in Europe checks out the profile, boom, they see the new name. Simple, clean, exactly what you'd expect. But then it happens. The transatlantic cable gets a little glitchy, and the network connection between the US and European servers just dies. A network partition has just happened. And user A's update? It's now stuck in the USA. It never made it to Europe.
So now we're at the moment of truth. User B in Europe has no idea that anything is wrong, and they try to load user A's profile. The server in Europe has to make a choice right now. What does it do?
And this is where the system's design kicks in. If it was built for consistency, we call that a CP system, it has no choice but to return an error. Why? Because it can't contact the US server, so it can't guarantee the data it has is correct. But if it was designed for availability, an AP system, it just sends back the old name. It serves the data it has, because getting a response is more important than being perfectly accurate. And that right there is the CAP theorem trade-off in action.
So, for our social media app, showing some old data for a bit is probably fine. But what about systems where the stakes are a lot higher? Let's look at how this choice is made when the consequences are, well, a lot more serious.
You absolutely choose consistency when being wrong would be a catastrophe. I mean, think about booking a concert ticket. You can't have 2 people booking the exact same seat, 6A, just because of a network hiccup. That's a disaster.
Same thing with e-commerce inventory. You can't sell that last iPhone to two different people. And you better believe financial systems need consistency, because a stale stock price could lose someone millions. In these cases, it is much, much better to be temporarily offline than to be wrong.
On the flip side, you choose availability, when being down is way worse than being a little out of sync. If you see your friend's old profile picture for a couple of minutes on social media, who cares, right? If Netflix shows you a slightly outdated movie summary, the world keeps spinning. For these kinds of systems, being responsive and always on is way more important for the user experience.
But here's where things get really clever. This choice isn't always for an entire application. A lot of times, a single app has different needs for different parts of its service. And a perfect example of this is a ticketing system like Ticketmaster. Just think about it for a second. When you're in the process of booking a specific seat, that one transaction, it absolutely must be consistent. The system has to guarantee that you and only you are getting that seat. But what about when you're just browsing the list of upcoming concerts? That part of the site can totally prioritize availability. A slightly old event description is a tiny price to pay for the website always being up and running fast. You know, this whole decision between consistency and availability isn't just some high-level philosophical debate. It has a massive, direct impact on a system's architecture and the actual technologies you use to build it. So if you're on team consistency, you're going to be looking at design patterns like distributed transactions, and you'll probably use technologies like good old Postgres or modern powerhouses like Google Spanner. Now, if you're on team availability, you're thinking more about having lots of copies of your data and syncing them up later. And for that, you'd use something like Cassandra or DynamoDB in its normal mode. Your choice directly leads you to a specific tech stack. And finally, just to add one more layer of nuance here, it's really important to get that consistency isn't just a simple on or off switch. In the real world, it's actually more of a spectrum with different levels and different guarantees. So strong consistency is the one we've been talking about, the ironclad guarantee that you're seeing the latest data. That's for your bank balance. But then you have things like read your own rights, where you are guaranteed to see your own updates right away, even if other people don't yet. And then there's eventual consistency, which is the default for most available systems. It just promises that, eventually all the servers will catch up and have the right data. And all of this leaves us with the one question you should always ask when you're designing a system. Does every single read really need to see the absolute most recent write? How you answer that question will guide every single technical decision you make, forcing you to find that perfect balance between correctness and the desire to always be on. And understanding that trade-off, well, that's the heart and soul of modern system design.